Okay, hello everybody. Let us start with the next part of our talk. Now that we realize that Debye considered only those waves which within the crystal boundary are forming these standing waves. Okay, so standing waves means it is something like that, it goes forward and backward, but these nodal points do not move with time. So it may be something like this, okay, and like this. So these all becomes zero. That means the amplitude of these waves, normal modes of vibrations of the arising out of the collective vibrational modes of the crystal, their amplitude is zero at the boundaries, and we will consider that the linear dimension is L, so L cube is the volume of the so that's why the analysis of the standing waves is necessary. All those other waves, other modes that in principle can be or may be generated, but they, while they are forward and backward movement, they will have phase differences in the manner that they will destructively interfere with each other, and thereby they will not be present finally in the crystal system. So we have to now find out that what are the number of, that is, we have to again find out G nu D nu, and that is the number of such normal vibrational modes with frequency between nu and nu plus D nu. Okay, that is what we are ultimately aiming. So for that, before we getting into that, we have to know that what is a traveling wave, how is it generally expressed, and then we can just have a look at how the traveling waves are represented, and that is represented by a function of x and t in one dimension. So in one dimension it can be represented like this, and then sine function kx minus omega t. This is the forward moving standing wave, and this is the oscillation of the amplitude that is shown for this wave. Okay, it's a perpendicular displacement, and a is the amplitude, which is the maximum displacement associated with the wave. And now it is in one dimension traveling wave. Okay, so a is amplitude of the wave, that is the maximum displacement that is possible, and then k is represented as 2 pi by lambda, where lambda is the wavelength of the wave, and then omega is angular frequency, and that is twice pi nu, where nu is the frequency, and then nu is again is equals to v by lambda. So the v is the velocity of the wave. Okay, so for light it is c by lambda, that is nu, frequency of light, where c is the velocity of light. Now let us get into this. Now this expression can be conveniently represented for mathematical convenience as something like imaginary part of a e to the power I kx minus omega t. See, the imaginary part of this is nothing but this, but exponential functions, operation of exponential functions mathematically is become more convenient, and that is why this is actually used. Now in three dimension this thing can be extended as r vector, positional vector, and t, and this is again the imaginary part of a and then e to the power I k dot r minus omega t. Okay, where again a is the amplitude, and then k is the referred as k wave vector, and the magnitude of wave vector is sometimes referred as k without that bar, and that is again 2 pi by lambda. Okay, and then 2 pi by lambda can also be written as twice pi nu by v, and then omega as it is twice pi nu. Okay, and as we said, the velocity of the wave v, and that may be represented as 1 omega by k, and that is essentially nu lambda. So these are the relationships. Okay, now this is a three-dimensional traveling wave. Okay, so these are the representation of traveling wave. in 3 dimension. Okay, for this one. Now how a standing wave is represented? When two traveling waves approach each other, the superposition of two oppositely moving traveling wave leads to the standing wave. So that means this one is the forward moving wave and the backward moving wave will be a plus omega t here, and that if we superimpose, then the standing wave is typically represented as as something like this: a e to the power I say k dot r minus omega t plus e to the power I k dot r plus omega t. Okay, so this part will automatically, suppose it is one dimensional, then it will be kx ikx, and that will lead to e to the power ikx and twice of cos omega t, right? Because e to the power e to the power minus I theta plus e to the power I theta, theta is omega t, and that will lead to cos omega t. So in this case also it will lead to this standing wave, then in general can be represented at something like twice a e to the power I k dot r and then cos omega t. Now the corresponding, to analyze, corresponding say 2a e to the power I k x cos omega t, it is in one dimension, suppose only for one dimensional standing wave. Then we know why is it called, why does it represent a standing wave? Because suppose this is the boundary and there is a wave, and you ensure that kx equals to say kl equals to n pi, where n equals to 1, 2, 3, etc. Then what happens is imaginary part of that. So we will consider u of rt for a standing wave as imaginary part of this quantity. Okay. So the alarm is there, so I have to continue it in the next video.